Hi, I'm Randy Dahlgren, Professor of Soils and Biogeochemistry at the University of California, Davis. This presentation is going to explore nutrient dynamics and water quality on California rangelands. California rangelands provide numerous ecosystem services, such as water quality, reservoir storage, recreational activities, wildlife activities, a very important function for grazing and supporting the beef industry, as well as carbon sequestration, and we are also now experiencing lots of fire at the wildland-urban interface, and this involves management of California rangeland forage as well. The primary nutrients of concern in California rangelands are nitrogen and phosphorus. Nutrient pollution exists from both natural sources, which includes bedrock and wildlife, as well as numerous human activities. The nutrient pollution for nitrogen is important in terms of the forms of nutrients. We have organic nutrients, which are not generally available directly to aquatic organisms. We have ammonium and ammonia, which are important sources of nutrients, as well as nitrate. The organic nitrogen gets transformed to ammonia and ammonium, which then gets further transformed by microbial activity to nitrate. Ammonium, being a cation, is generally held on the soil and is not relatively mobile compared to that of nitrate, which is relatively mobile and often ends up into our stream ecosystems. But both ammonium and nitrate are readily available to aquatic organisms such as algae. In terms of phosphorus, we have also organic forms, such as the colored material we see here in the beakers. We have phosphate that is adsorbed to particles like iron oxides, and then we have dissolved phosphate, which is dissolved in the water column. The phosphate is readily available to aquatic organisms, and also a portion of this adsorbed phosphorus is available as it desorbs to the water column and becomes available to the aquatic organisms. Excess nutrients can cause several different concerns in aquatic ecosystems. On the left here, we show advanced eutrophication, and when the algae dies, it is consumed by the microorganisms, and it lowers the dissolved oxygen concentrations, which can have dramatic effects on the entire aquatic ecosystem. Harmful algal species produce toxins, which are toxic to both for drinking water purposes as well as for recreational activities. And in areas with concentrated animal activity, such as feedlots, the ammonium, which is generally held on the soil particles, can be eroded into the waterways, and the ammonia can cause direct toxicity to a number of aquatic organisms, including fish. Within the state of California, several areas have been identified with nutrient impairment, with the possibility of grazing being the source of the nutrients. In particular, we have a source here in northeastern California in the Cascade Range, and then along the coast in the coastal range. However, it must be recognized that background concentrations of nutrients are not zero. There is a naturally occurring background level that occurs in all ecosystems. And in fact, aquatic ecosystems require nutrients to maintain their productivity. In terms of eutrophication concerns, there are various standards set for nitrate and phosphorus, as shown in the right-hand column here. But background levels of nutrients are not zero. In terms of nitrogen inputs into California rangelands, atmospheric deposition is a major player. This graph here shows the amount of nitrogen being deposited into ecosystems in California from the atmosphere. And for most California rangelands, the values range from about 5 to 10 kilograms per hectare per year. If we look at the amount of ammonium and nitrate being exported from watersheds here in kilograms per hectare per year, for a long-term record in the Sierra Nevada foothills, we find that there's considerable variability in the amount of nitrogen exported each year, with a mean value of 1.6 kilograms per hectare per year. So generally, we have 5 to 10 kilograms per hectare per year coming in from the atmosphere, and only 1.6 kilograms per hectare per year leaving in the stream water. This means that most California rangelands are sinks rather than sources for nitrogen. There's also several natural sources of nutrients that have been identified here in California, and one is in the Cascade Range associated with volcanic springs. The big springs on the Shasta River of Northern California has nitrate concentrations of nearly 0.5 part per million and phosphate concentrations on the order of 0.1 milligrams per liter, all coming from natural sources. Similarly, nitrogen is commonly found in sedimentary rocks in California. In a survey of nearly 1,000 rocks in California, concentrated in the sedimentary rocks of the California Coast Range, we found concentrations, median concentrations of 426 parts per million in rock. And these were clearly identified as being highest in the sedimentary rocks in the Coast Range. And if we overlay then the watersheds that have nutrient impairments, we see that most of the areas with nutrient impairments are found on these sedimentary rock landscapes. So the rocks could be contributing a large part of the nutrients here. California rangelands also are naturally susceptible to leaching of nitrate. This graph shows the nitrate concentrations over a 4-year period of time here. And we find maximum concentrations occurring in January of each year, and then as the growing season kicks in, the nitrate concentrations are decreased to very low levels in the spring and summer months. This occurs due to a temporal discoupling of the nutrient cycles. In January of each year, the oak trees have deciduous oak trees have dropped their leaves. They're not taking up nutrients from the soil. And the annual grasses have just germinated and likewise are so small they have not taken up many nutrients. Therefore, the nutrients that have accumulated throughout the summer months and the fall within the rangelands here are flushed out by those early season rains in January. As the season progresses and the oaks leaves bud out and the annual grasses become active, they take up a large portion of the nutrients from the soil, preventing their leaching into the stream water. Therefore, California oak woodlands and annual grassland are naturally susceptible to seasonal nitrate leaching due to this temporal discoupling between the availability and the demand for nitrate in the ecosystem. A statewide survey of 24 rangeland streams in California was conducted in 2000 and 2001 for several California rangelands, as shown by the map here. Nutrient concentrations are shown here in box plots, showing the distribution, with the 50th percentile here being the median concentration observed for the 24 sites. And this involved a total of nearly 1,000 measurements. For most of the constituents here, they were the median concentrations were very low, very near background concentrations, with very few median concentrations being greater than the concerns for eutrophication. Therefore, when we measure the California rangelands, we see very little evidence of excess nutrient leaching off of these rangelands. A study was conducted to look at the effects of grazing intensity on nitrate leaching. We had 4 different treatments ranging from no grazing to leaving of 1,500 kilograms of residual dry matter. That's the amount of forage left on the landscape. 1,500 kilograms per hectare of residual dry matter. We did this by grazing entire watersheds and collecting the water draining throughout the year. This graph summarizes the grazing impacts here for nitrate, again in milligrams per liter. The median values, again, are the lines through the bars here, through the boxes. And what we find is median concentrations for the no grazing, 1,500 and 1,000 kilograms per hectare of residual dry matter were very low. In fact, they are lower than the concerns for eutrophication. However, when with higher grazing intensity, leaving only 500 kilograms per hectare of residual dry matter, then the median concentrations did increase quite dramatically. So this really shows that the grazing intensity has a big effect on the potential for nutrients leaving the watershed through the river system. This is a diagram here showing all the data points we collected for the 500 pounds per acre residual dry matter. Nitrate is shown on the right-hand graph here and is represented by the red dots, where the stream flow is shown on the left axis here in cubic feet per second, with the blue bars here representing how much water was flowing out of the river at any particular time. I want to make 2 points here. First, seasonally, we see a long-term decrease in the amount of nitrate leaching out of the system. And this is due to that temporal discoupling of the nitrogen cycle. Early season rains are flushing out the nitrate when the trees and grasses are not taking up the nitrogen, but later on in the season, concentrations are much lower as plants are removing nitrate from the soil, preventing its leaching. Second, I want to point out that the concentrations of nitrate vary dramatically during a storm event. As the hydrograph goes up and down the blue line here, we see that we get generally the highest concentrations of nitrate leaving the systems at the peak of the storm event. Therefore, monitoring of water quality on California rangelands is very difficult because the concentrations change very dramatically throughout the season as well as throughout a given storm event. In terms of beneficial nutrient management practices on the landscape, grazing management is a very easy practice that has big impacts. By maintaining residual dry matter on the landscape, it promotes the infiltration of water so that the soil is able to act as a nutrient buffer. Also, putting in buffer strips, especially along perennial streams, is important. A short buffer strip also has the ability to remove lots of nutrients, pathogens, as well as sediments, and preventing them from getting into the stream water. And if cows are allowed to access the stream, it deteriorates the physical quality of the habitat, as well as allows direct input of nutrients from their feces. Another practice that has been used in irrigated pastures in California is using small flow-through wetlands to process the water before the tailwaters before the water gets into the major streams. Here, water was applied to the irrigated pastures and the higher elevations here. The tailwaters ran off and went through the wetland here at the bottom. And if we take a closer look at the wetland, we see some water here, but we see lots of vegetation here, which is able to both filter out and uptake nutrients, pathogens, and sediments. If we look at the efficiency here of the wetland, these bars are showing the percent reduction in the amounts of various water quality parameters here. So for the nitrogen and phosphorus species, about 40 to 60% of these nutrients were retained within the treatment wetland. And the water only was maintained in the wetlands for a matter of about 30 minutes. So this was an appreciable reduction in nutrients. Also, for E. coli, which is an indicator of potential pathogens and sediments, the efficiency of these wetlands was ranging from 60 to 80% reductions on the amount of E. coli and sediments input into the waterways. So in conclusion, most California rangelands are sinks rather than sources for nutrients. Background concentrations of nutrients are not zero. There are several natural background sources that are contributing nutrients in the absence of human activities. California oak woodlands, annual grasslands are naturally susceptible to seasonal leaching of nitrate due to the temporal discoupling of nitrogen availability and demand. Rangeland streams rarely exceed nutrient thresholds for eutrophication, except during large storm events. and accurate nutrient monitoring of rangelands is extremely challenging given the temporal variability that exists in leaching of nutrients from the landscape.
You can find more informative presentations covering ranch water quality topics on the UC Rangelands website, and look for the Water Quality Information Hub or direct your web browser to the URL shown on this slide.